Okay, I'll talk about the SSL certificates in the Ethereum blockchain, and I'll propose our system which we designed and implemented on the blockchain, which proposes truly authoritative certificates. Okay, so truly authoritative certificates for secure web browsing using the Ethereum blockchain. So in order to start with, I'll briefly give you an introduction to the PKI, public key infrastructure, and how the web certificate model works. So every day in our daily lives, we all use the HTTPS protocol to make secure connections to the website we visit. This protocol provides message integrity, confidentiality, and server authentication. The server authentication itself relies on a client's ability to obtain the correct public key which is bound to the server. And in order to provide this, the current WebCA model uses a set of certificate authorities, which we refer them as CAs. And these are companies or businesses that they issue certificate for all of the domain names over the web. And like how it works is they receive certificates requests for domain names from everyone. And then they have to verify the ownership of this domain. They have to make sure the person who's asking a certificate for that specific domain name is the real owner of that domain, is the authoritative party. And this is the main step of issuing the certificates. And once the verification is done, they issue the certificate for that domains. And by issuing, we basically means they bind a public key to that domain so that it secures further communication to that server. But PKI is not perfect. Recent security incidents shows that there are some issues with public key infrastructure. The first one is CAs have been focus of targeted attacks. Like during the last few years, for example, Komodo and DigiNotar, which are the two significant CAs, they have been attacked by an attacker where they were able to issue themselves the fraudulent certificates for top-level domains such as Google. The other issue is we know very little about CAs, and I know there has been work done in the CA ecosystem, but our knowledge in the full spectrum of web CA model is very limited. And what is not clear yet is we don't know how many CAs actually issue certificate to the client over the web. And the other issue is intermediate CAs are invisible. They have two kind of CAs that issue the certs to the public, root and intermediate. The problem with intermediate ones are they are all over the web and they're invisible. There's no way for us to know them. And the only way for us to get a list or enumeration of these CAs is to scan the entire web, which is not an easy task to do. So those were my the motivation of our work. This is the roadmap of my talk today. First, I'll show you the empirical study that we performed on the CA ecosystem. Based on the results we found, we start rethinking the authorities concept in the PKI, and we were able to decentralize public key infrastructure for the web. We created and implemented an Ethereum-based application for issuing certificates, and at the end I'll show you the performance and security evaluation of our system. Okay, so here is the methodology of our empirical study. It has three main steps. In the first step, we have to identify all the existing CAs over the web, and by all the CAs I mean both root ones and intermediate ones. In the second step, what we did was we identified the companies, and by the term companies I mean all those CAs that actually issue certificates to the public. And at the end, once we have a list of companies, we start domain control validation analysis. So for the first step, we started with the root ones, and we retrieved the list of root certificates from Microsoft, Apple, and Mozilla. After merging all of this data together and collapsing different identities for the same CAs, we got a list of 259 unique root CAs. And for the intermediate ones, as I have mentioned before, there's no way for us to get that except for scanning the web. So what we decided to do was we used the research, the result of other major research projects, such as Google Certificate Transparency, ZMAP, and EFF. And by merging all of these, we got a list of around 446 actual unique intermediate CAs. So now that we have all of them, we have to find out among 700 CAs, how many of them are issuing certificate. And we manually research all of these certificate authorities, and we found that only 223 of these certificate authorities are acting as companies and they're issuing certificates to the public. So now is the time to do the domain control validation analysis. What we did was we created our website. We bought our domain name. It was a website for registering the workshop. So every user has an account there. They have their username, password. They go there, they put their credit card information and register for the workshop. So it was a legitimate website which required certificate. And I started buying one regular 1-year single domain certificate for this domain that we have from each and every 223 companies. So as a result, we were able to provide a very comprehensive enumeration of all the companies that we had. These results contains of the number of companies that directly issue certificates, the cost of certificates, the country or information that needs to be provided to these CAs to get a certificate. And we also found that among these 223 CAs, only 71 of these are willing to issue certificates. And among these 71, 42 of them propose domain control validation certificates, which is not a very good thing here, because like in the term of like when the CAs want to issue domain control validated, they're not really authoritative over who owns what domain. And actually, VeriSign, which is a very big CA, is not more authoritative than you and I in terms of validating these domain names. So how do they do this domain control validation? They rely on indirection. And in order to know what do I mean by indirection, let's look at the email-based validation, which is the most common way of like proving the CA that you own domain.ca. So in this case, the CA would send you an email. This email contains a secret validation token, and they send it to some email address that they assume is controlled by the actual domain owner. Here is, for example, admin.domain.ca. So let's dive into the detail how this email validation works to see what do I mean by indirection. So in order to send a validation email, CA requires the IP address of the corresponding mail server. So what do they do is they would consult with the corresponding DNS, and they get the error code and IP address. But look at here, like this error code has been placed into the DNS by some registrar, and there's a person out there who has the password to this registrar, and they can log in and control. That's fine. CA got the IP address. Now it sends the email, the validation email, which contains the secret, will go to the corresponding mail server. Again, there is another person here. He or she has the password to this mail server, and they can log in. So at the end, the email would end up in somebody's mailbox. We hope it's the domain owner. And this person can log in, has password to this email account. They can log in and retrieve the secret validation token, which is supposed to be confidential. So once she or he can get access to this secret, means that the domain ownership is verified. But if you look at this whole email-based validation, we can see that there are 2 levels of indirection, and for each level there are some vulnerabilities that can be leveraged by the attackers. For example, both sites, as I have showed before, they're password protected, so the attacker can break the password and log in and break the validation. The other one is CA needs to have a good view of the DNS, and if the DNS was attacked by an attacker, again, attacker can get himself a fraudulent certificate. The third one is validation email. As I have mentioned, they're contained secret validation tokens, so confidentiality matters. But unfortunately, SMTP protocol uses opportunistic encryption, which is not really secure against active adversaries. And the last one is, as I have mentioned, CA send the validation emails to some default email addresses that they assume it's controlled by the domain owner. But sometimes the domain owner do not even know that these email addresses exist, and they're being used by some CAs for the purpose of validation. So it's very hard to hold in reserve these kind of email addresses. So what we did was we used the blockchain as a new paradigm for PKI. I'm not going to go through the blockchain introduction because you have already heard from my supervisor. But what we did was we used this to build a PKI. Just imagine if PKI were added to the blockchain, who would be authoritative over these domain names? When domain names themselves are issued through the blockchain, so the blockchain is the authoritative party. That's why we called our system a uni-authoritative paradigm, and it successfully resolved indirection and authority issues. It's called Ghazal. It's a smart contract-based naming and PKI system. It's built on the blockchain, Ethereum blockchain, and it enables users to fully manage and maintain control of their domain names, and they don't have to rely on any trusted third party like CAs. They're authoritative. And because it's decentralized, names cannot be reassigned without the cooperation of this owner, which is a great feature, I think. So what the users can do in our system, first they can register domain names, and we have registration fees which are against domain name squatting. They can also renew their domain names. How we design our system is using Ghazal. When domain name expires, they still continue to function, but the owner loses the sole control over this domain name. So anyone can come and grab the domain by paying the registration fee. So the domain owner needs to repay the registration fee to be able to control the domain. And they can also transfer the domain names. Transferring can be done using the auction or by calling the transfer domain function. Auction is where we leverage the programmability of the Ethereum blockchain. So we used inheritance. We created a child contract of our main contract, and it adds the auction process. So using the new, like the Ghazal Star smart contract, users can run any number of auctions on any number of domain names they have. Here is a piece of code where we implemented the auction. As you can see here, we have states, like any auction can be either in open or locked or ended states. And we have a mapping data structure called auction list, which stores each and every auction with all of its features. The other way of transferring a domain name is by basically calling the transfer domain function. And like transferring the domain name at the Ethereum level means just like changing the Ethereum address that controls the domain name. So they can simply call this function and provide it with a new address they want to transfer the domain name to. And they're free to decide to either transfer its associated attributes or not, such as certificates. Here's again like a piece of code where we implemented the transfer. As you can see, we have three modifiers. Modifiers in smart contracts, like they apply certain conditions when you want to call the function. So here, when the domain owner calls the transfer domain function, it checks like some conditions. For example, the domain should not be in unregistered or expired state, or like it should be only the domain owner who can transfer the domain name. They can also assign arbitrary data. I mean, by they, I mean domain owners. They can assign arbitrary data to their domain names, and because this system is built on the blockchain, the value are globally readable, they're non-equivocative, and they're not vulnerable to indirection attacks, of course. So these values include the TLS certificates. In our implementation, we use dynamically sized arrays, so users can assign as many certificates they want. This is for the purpose of load balancing. They can also add DNS zone files. Here is to add the resource records to their domain name. But because, as Jeremy mentioned, it's not very economically efficient to store a big data on the blockchain. So what we decided to do is the user would add the DNS zone file, like they can put it anywhere they want on external servers. And they put the hash of the DNS zone files and also the IP address of the server that hosts that files for further file verification. So Ghazal, our system was implemented in 370 lines of Solidity language. The Solidity is a language of smart contract. And we tested it on the Ethereum test network, and we could build a cost evaluation table. So here is, as like you can see, like it's very cost effective because, for example, to register a domain name in our system, the user would only pay $3.50. Whereas in the real world, they have to pay $20 per year. Or, for example, to get a certificate for the domain name they have, they need to pay only $1.43. while in real world, the cost for getting a certificate is $80 per year. So it's very cost efficient. And we also used a security analysis tool, Oyente, to test our smart contract against known security issues like the reentrancy vulnerability, also known as DAO bug, which we all heard about. And as you can see, like all of these falses here show that our smart contract is not vulnerable to any of these vulnerabilities. And yeah, these are the future works that we can work on it more. For example, we can like work on the scalability, understand like how to minimize of like the amount of data the users need to fetch when they want to look up the domain names, or we can build a user interface for this system, because now it's working on the Ethereum level. You have to go through the Ethereum wallet or whatever like client you have. And because our system is built on the Ethereum, we have the programmability feature, so there are a lot more functions to be explored. And auction is one of them, but we can still explore more functions on it. Yep, thank you.